In this video, we're going to cover sections 5.1 and 5.2, and we're going to be learning about exponents. And in section 5.1, we're going to specifically be learning about how we can use exponent rules to simplify exponential expressions. So first of all, just a review of what exponents are. If we have an exponent like 3 to the 5th, an exponent is just another way of writing repeated multiplication. So 3 raised to the 5th power means to multiply 3 by itself 5 times. So notice we have 1, 2, 3, 4, 5 3s. And so if we want to evaluate some of these, this first one means to take -2 times itself 4 times. And because we have a negative and there's an even number of negatives, we know that this is going to be a positive. So this is going to be a positive 16. And that's different than the next one, because the next one is just 2 that's raised to the 4th with a negative out in front. So it's just 2 times 2 times 2 times 2, which of course is 16, but then that negative in front makes it a negative 16. So the parentheses do make a difference. The next one we want to look at is one that's, what do we have when we have a fraction? Well, it's the same idea. 2/3 squared means we take 2/3 times itself twice. We know when we multiply fractions, we just multiply straight across. So 2 times 2 is 4, and 3 times 3 is 9. And there we have it. So that's just a review of exponents. Now we're going to move into some rules here. So the first problem I want to consider is what happens when we have 7 to the 4th times 7 squared. So we multiply an exponent times an exponent. And remembering our rules, this was 7 times 7 times 7 times 7. That was the 7th to the 4th. And the 7 squared is 2 more 7s. So altogether, how many 7s is that? 1, 2, 3, 4, 5, 6. So this is 7 to the 6th power. And so the idea here is that when we multiply exponents, what we do is we add the powers, because 4 plus 2 is 6. So in general, if I have x to the m times x to the n power, this is x to the m plus n. When we multiply exponents, we add the powers. And so we can do that in each of these examples. This first one would be 5 to the 9th power. We're going to add 4 plus 5. The next one would be x to the 10th power, because 3 plus 7 equals 10. And then the last one, even though we have 3 exponents here, that's okay. This is going to be 4 raised to the 5 plus 2 plus 6, which of course is the 13th power. So this is 4 to the 13th power. That's how you use the product rule. Now, there are of course other rules. So the next one is we now have a power raised to a power. We have 4 to the 3rd squared. And so just using our definition of exponents, this would mean 4 to the 3rd times 4 to the 3rd, right? And of course each one of those, because it's 4 to the 3rd squared, and then each one of those 4 to the 3rds is 3 4s, so that's 4 times 4 times 4. That's the first 4 to the 3rd. And then the next one is also 4 times 4 times 4, which now brings up how many 4s? 1, 2, 3, 4, 5, 6. So this is 4 to the 6th power. And if you notice, to get to 6, we must multiply the powers. We take 3 times 2 to get 6. So when we raise a power to a power, like in this case 3 to the 2nd power, when we raise a power to a power, we don't add the powers like the last one, we multiply the powers. So in general, if I raise x to the m to the nth power, that's the same as taking x to the m times n. You multiply the two powers. We have a couple examples here. So this first one would be 3 to the 4 times 5, and 4 times 5 is 20, so this is 3 to the 20th power. Next one, we raise a power to a power. We multiply them, so this is x to the 14th power. Two times 7 is 14. Okay, we have another type of problem to consider here. We have 5y raised to the 4th. Well, we know this means we take 5y times 5y. 5y times itself how many times? 4 times. And we can see here that this is 1, 2, 3, 4, 5. So it's 5 to the 4th. And then how many y's? 1, 2, 3, 4 y's. So y to the 4th. And then you could rewrite 5 to the 4th. 5 times itself 4 times is going to be 625. So this is 625y to the 4th. And so the little note here is that the power of a product, so we had a product, we had 5 times y, that's a product. And that product is raised to a power. So the power of a product is the product of the powers. And kind of the easiest way to think about this is almost like you're distributing the power. The 5 got raised to the 4th power, and the y got raised to the 4th power. So in general, if I have bases x and y, x times y raised to the nth is the same as x to the nth times y to the nth. So a couple examples here. This would be like 7 squared times x squared. And of course 7 squared is 49, so this is 49 x squared. We have another example. Here our product has 3 different parts, so this would be the 3 has to be raised to the 4th, the x has to be raised to the 4th, and the y has to be raised to the 4th. 3 to the 4th is 81, that's 3 times 3 is 9, 9 times 3 is 27, and 27 times 3 is 81. This gets raised to the 4th power, and then the y gets raised to the 4th power. There you go. A few more examples here. So we have another power of a product. This next one, remember, everything inside those parentheses is now going to be squared. So this is negative 1/3 squared. And then x to the 3rd has to be squared, and then y squared has to be squared. Now, negative 1/3 squared, remember that's negative 1/3 times negative 1/3. And the negative times a negative is a positive. And then we know 1 times 1 is 1, and 3 times 3 is 9. So this is 1/9. Now remember, we have a power raised to a power, so that goes back to one we just talked about. It's the power rule right here. Power raised to a power, remember we multiply the powers. So in this example, we're going to have 3 times 2, which is x to the 6th. And then we have another power to a power. 2 times 2 is 4, so this is y to the 4th. There's that one. So I have one more example here. This is another one where we are going to be raising powers to powers. So 5 raised to the 2nd, that's multiply the powers, so that's x to the 10th. And then again, the x to the 4th raised to the 3rd, multiply 4 times 3, we get 12. And now we have an exponent times an exponent, which is the product rule. That was the first one we talked about. The product rule, when you take an exponent times an exponent, you add the powers. So when I add 10 plus 12, I get 22. So this is x to the 22nd power. Okay, so a new type of rule to consider here. What happens when we divide exponents? So this is like we have 1, 2, 3, 4 x's on top, and then how many x's on bottom? 2 x's on bottom because it's x squared. And now then we could say, okay, we have some common factors here. We have 2 pairs of x's that can divide out from the top to the bottom, which leaves how many on the top? Well, it leaves 2. And it leaves nothing on the bottom. It just leaves 1 on the bottom. So this is essentially x squared over 1, or x squared. And the kind of shortcut here is, the way that we get that power of 2 in our answer, x squared, is we subtract the powers. So if you take 4 on the top minus 2 on the bottom and subtract it, you get 2. So when you divide exponents with the same base, we subtract the powers. So x to the m divided by x to the n is x to the m minus n. It's the opposite. When we multiplied exponents, we added the powers, but when we divide exponents, we subtract the powers. So example A here, this would be x to the 10 minus 4. 10 minus 4, of course, is 6. I also just like to think about these as, you have 10 x's on the top, you have 4 on the bottom. If you cancel the 4 on the bottom with 4 of the ones on the top, that leaves 6 left, so it's x to the 6th power. Okay, then we also have one more of these. Now with the numbers, those aren't exponents. The 32 and the 16, those are just straight numbers, so we divide them like normal. And we know that 32 divided by 16 is 2. So this is going to be 2. And then we have C, we have 4 on the top, minus C to the 1 on the bottom. And D's, we have 12 on the top, minus 6 on the bottom. So simplifying, this is going to be 2. 4 minus 1 is 3, so C to the 3rd power, and D to the 6th power. That's that example. We also have the power of the quotient rule. Just like we had the power of a product. So what happens here is both the x and the y get raised to the n power. So an example here, this first one would be x is raised to the 2nd power, and 5 gets raised to the 2nd power. And of course 5 squared is 25. So this can be rewritten as x squared over 25. Same thing goes for the next one. This would be 2 cubed over a cubed. Both the 2 and the a get cubed. And 2 cubed is 8. 2 times 2 times 2 is 8 over a cubed. Okay, another one. Consider the example 3 squared over 3 squared. Well, if I use that same quotient rule that we just talked about a few examples ago, we know that we would subtract the power. So this would be 3 to the 0 power. What is the 0 power? That's kind of a strange problem. Well, another way of thinking about this is 3 squared over 3 squared is 3 times 3 divided by 3 times 3. Remember, we can divide out those common factors. And so what's this going to be left? This is going to be equal to what? 1 over 1, which of course is just 1. So anything raised to the 0 power is 1. For any base x, x to the 0 power is always 1. So 10 to the 0 power, that's 1. This whole quantity, 3x to the 5th y squared raised to the 0 power, that whole thing, strange enough, is 1. It's kind of a neat one to remember. And that does it. So That's 5.1. Now in 5.2 we get to talk about two things. We get to talk about negative exponents and scientific notation. And so when we have negative exponents, there's a couple rules you want to remember. And basically, when we have a negative exponent, we want to make that exponent positive. And the way you do that is if it's on the top, because this is like x to the minus n over 1, then we're going to move that x to the minus n to the bottom. So it's going to become 1 over x to the positive n. And if that negative power is on the bottom, it's going to move up to the top and become a positive power. So we have some few examples here where we want to change the exponent to a positive first and then simplify. So this first one, if I want to change it to positive 2, it's going to have to be 1 over 3 squared. 3 squared is 9, so this is 1 over 9. Now in the next one, the thing you have to be careful of is that this negative 4 is only attached to the x. So if I want to make that power of negative 4 positive, only the x part goes to the bottom. The 5 is going to stay on top. The x to the 4th goes to the bottom. So this is 5 over x to the 4th. And we can apply that same principle in the next example. Only the exponents that are negative will move. So, for example, the 5 is to the negative 2 power, so if I want to make that positive, that's going to have to go to the bottom. Same goes with the x. X is to the negative 8, so to make that positive, I make it a x to the 8 on the bottom. On the bottom, I have y to the negative 5. I want to make that positive, so that's going to be y to the positive 5 on the top. And then z to the 4th is already positive, so I'm going to leave that on the bottom. So that's how you make negative exponents positive. Well, I guess the only other thing we could do there is 5 squared, of course, is 25. 5 times 5. So I could rewrite this as y to the 5th over 25, x to the 8th, z to the 4th. Okay, one more of these. Actually, I guess we have a few more. Example D. Now here we have a couple things going on. There's a couple different ways we could approach this. I think probably the easiest way is right off the bat to use the product rule. Because we know when we use the product rule, we add the powers, right? So if we add the powers, this is going to be b to the 7 plus the other power, which is negative 19. And if I add a 7 and a negative 19, that's going to be a negative 12, which is still a negative power, which we don't want. So if we want to make it positive, we just have to move it to the denominator. And that's how we treat that. Of course, the other way we could think about this is we could, right off the bat, this is option number 2, is we could move the 19 to the bottom. This is a negative 19. This is kind of the other way of doing this. And then we can subtract the power. 7 minus 19 is negative 12, which of course is 1 over b to the positive 12. Either way gets you the correct answer. One way is not more correct than the other. Okay, we also have example E. So remember, this is when I have a product here raised to a power, everything inside there has to be raised to that power. So this is 3 raised to the negative 3rd power. This is x to the negative 7 raised to the negative 3 power. And this is y to the 6th raised to the negative 3 power. I'm going to rewrite the 3 to the negative 3 for now. Remember, when we raise a power to a power, we multiply these. So we have a negative 7 times a negative 3. That's a positive 21 as a power for x. Then we have y. 6 times negative 3 is negative 18. Now, one of the most common things I see people want to do here is take this and say, oh, that's equal to negative 27 somehow. Because they see 3 to the third and they think, oh, that's 27, and that negative power must make it negative. But no, this is not the case. I don't want to do that. Please do not do that. Instead, like always, make that power negative. So make that negative power positive. So if I look at this expression, the 3 to the negative third is negative. So to make that positive, it goes to the bottom. And the same goes with the y. That's going to be a y to the positive 18 in the denominator. And then the x to the 21 stays positive on the top. And this will simplify down to x to the 21 over, now 3 to the third is 27, y to the 18th, and there you have your answer. One last example here with these. If I'm simplifying this, I have a to the 10th over a to the 4th. Remember, we can subtract powers. So this would be a to the 6th. I have b essentially to the 1 minus b to the 7th. That's b 1 minus 7 is negative 6. And then I have c to the 6 minus 7. 6 minus 7 is negative 1. And then those negative powers, we can move those to the bottom. So that's a to the 6th over b to the 6th over c to the 1, or just c. So we could actually leave that 1 off. We get our answer, a to the 6th over b to the 6th c. Of course, another way to think about this is use that idea of what's on the top and what's on the bottom. I have 10 a's on the top, 4 on the bottom. 4 of those ones from the bottom will cancel with 4 from the top, leaving 6 extra a's on the top. And with b's, I have 1 b on the top, 7 on the bottom. That would leave 6 b's on the bottom if I canceled 1 from the top and the bottom. And then with the c's, I have 6 c's on top and 7 on bottom. If I canceled 6 c's out from the top and the bottom, I would be left with 1 c on the bottom. Just kind of another way to think about it. Okay, now the last thing that we're going to be talking about is scientific notation. Now, what is it used for? Well, a lot of times it's used in science as a better way or another way of writing really big or small numbers. It's a way to write really big or really small numbers. So we're going to do some examples and I'm going to teach you what we mean by that. The number is written in scientific notation if it has the form a times 10 to the b power. Notice it has to be greater than or equal to 1 but less than 10, which means it has to be a number that is a single digit number. It can have a decimal part, but the a part has to be between 1 and 10. So it can't be 10 or above. And then b has to be an integer, so which means b has to be a whole number, but it has to be a positive or negative one. And there's really only 2 concepts you need to remember here. And that is this. That is that when you have a big number that you want to write in scientific notation, you need to think positive powers or positive exponent. And then on the flip side, if you have a really small number, you need to think negative exponent. Big number, positive exponent, small number, negative exponent. So if I'm looking at this first example, 4,810,000, that's a big number. big numbers, we think positive exponent. So here's what we have to do. We need to count the number of decimal places. We need to move this number. 4,810,000, the decimal place here is going to be after the 0. And so I need to move it 1, 2, 3, 4, 5, 6 places. I need to move it 6 places. And when I move it 6 places, it turns into 4.81. We're thinking scientific notation here. So it's going to be that number A. So 4.81 is like my number A. And then it's always going to be times 10. And because it's a big number, we think positive exponent. And how many places we move? We move 6 places. So this is going to be to a positive 6 power. 4.81 times 10 to the positive 6 power. And if you think about what we're doing here is we're taking 4.81 and we're multiplying it by 10 6 times, which has the same effect as moving that decimal place over 6 times. And we can go backwards. So if I have the number 3.05 times 10 to the 5th, well, this is a positive number. Okay, that's positive. So we think big number. We have a positive exponent, that's a big number. So if I want to make this number big, am I going to move the decimal to the left, or am I going to move it to the right? Everybody hopefully should be thinking move that decimal place to the right. So it's going to be 1, 2, 3, 4, 5. And I move it 5 places because it's a positive exponent. And I want to make it a big number, which means I need to add in 1, 2, 3 zeros. And so this number is actually, let me rewrite it cleaner, this is 305,000. A few more examples here. The next one is 4.73 times 10 to the negative 3. That's a negative exponent, so we think small number. If I want to make 4.73 a small number, now I'm going to move the decimal place to the left. So I'm going to move 1, 2, 3 places to the left, which means I have to add 2 zeros. And so that's my number. I'm going to rewrite it here. This is 0.00473. The next example says to take the number 0.0000526 and write it in scientific notation. So as we have seen in the previous examples, we have to take this 526 and we know that it needs to be written as 5.26 times 10, and here is where we need to count how many decimal places were moved, just like the previous one. So we're moving here 1, 2, 3, 4, 5 places. And is this a small number or a big number? This is a small number. Small number means positive or negative exponent. Small number means negative exponent. So that's what our answer is going to be. Our answer is going to be 5.26 times 10 to the negative 5 because we moved 5 places and it is a small number. And that's just working with scientific notation. Sometimes we do need to do some operations with this. And really the easiest way, you could do this by hand, but the easiest way to do this is with a calculator. So I'm going to pull up my graphing calculator. You don't have to have a graphing calculator to do this. But the easiest way to do it, scientific notation, it has every calculator, most of the time will have one of these EE buttons, which takes the place of times 2. So when I see the EE button, that's like the times 10 part. I mean the same thing. Those are the same. So when I'm putting in my calculator, if I want to multiply 4.3 times 10 to the 6 times 1.6 times 10 to the negative 23, I'm just going to type in this. I'm going to go 4.3 and then EE. Now that's right above this comma button, and it's in yellow. Because it's in yellow, I have to hit second first. So I'm going to go second E, and that again, that means times 10 to the 16, and then I'm going to multiply that times 1.6, then E again, so I go second E, and now negative 23. Different calculators, the negative is in a different place. Just please don't confuse that with the minus button. The negative button on a graphing calculator is right below the 3. So this is going to look like 6.88 e to the negative 7. Remember that means times 10 to the negative 7. So this is going to be 6.88 times 10 to the negative 7. Nice to be able to let your graphing calculator do that for you. I can also do division with the graphing calculator. So I can do this next example. 1.2 e to the 5th divided by 4.8 e to the negative 7. And this is 2.5 e to the 11th, or 2.5 times 10 to the 11th. This equals 2.5 times 10 to the 11th power. One last problem is a word problem. It says the speed of light is 1.86 times 10 to the 5th miles per second. How long will it take time to travel 1,000, or I'm sorry, that's million, that's trillion, 13,950,000,000,000 miles. That's a long distance. And this is essentially a distance equals rate times time problem. Distance equals rate times time, where we're given a distance and we're given a speed or a rate. So I have, and it says how long. That means I'm trying to figure out what time is equal to. So I could solve this equation for time by dividing both sides by r. Divide by r, divide by r. R's cancel. And what you get is you get t equals the distance traveled divided by the rate. Now in this case, the distance, I want to write in scientific notation. I know it's that 13 trillion miles, but that's the same as 1.395 times 10 to what? Well, this is 3, 6, 9, 12, and one more 13. So this is times 10 to the 13th power and divided by the rate, which is 1.86 times 10 to the 5th. So if I put that one in my calculator, I get 1.395 e to the 13th divided by 1.86 e to the 5th. And that equals, according to this, looks like 75 million. So this is 75, 6 more zeros added on the end here. And of course that's time, so this is going to be in seconds. So this is 75 million seconds. Or also 7.5 times 10 to the 7th power seconds. And make sure you have those units on there. You know it's 7th power because this is 1, 2, 3, 4, 5, 6, 7 places. There you go. This is scientific notation, and that concludes the video. We'll see you in class.